Okay, hello and welcome everybody. Today we'll listen to Ida Arvidsson giving a talk about some of the challenges in AI-driven medical image analysis. This is RISE Learning Machines seminars. RISE is Sweden's research institute with nearly 3,000 people working on a wide array of topics. The computer science department works on applied AI projects for the benefit of society, and we organize these weekly learning machines seminars. These meetings will be recorded, and if you want to be removed from this recording, let us know by dropping me an email. Also, make sure to check out the collection of great talks that we have on our YouTube channel. Today, I have the pleasure to introduce Ida Arvidsson, who is a postdoctoral researcher at Lund University in the Division for Computer Vision and Machine Learning. Ida obtained her PhD in applied mathematics in 2021 with a thesis titled Applications of Deep Learning in Medical Image Analysis, Grading of Prostate Cancer and Detection of Coronary Artery Disease. The main research topics are deep learning applied to medical images, and the topic today is applications of AI in medical image analysis. And with that, I will stop sharing and hand over the word to you, Ida.
Thank you. So I hope you can see my screen now. Yes. And thanks for the nice introduction, and thanks for inviting me to present some of my research here. So as Olof said, I'm a postdoc, and I'm working with AI or mostly deep learning for analysis of medical images. And today I will talk about some of my research projects, and some of this will be ongoing work, so I might not have any final results for all of the projects, but I still want to give you an idea of which projects we have. And also, if you have any questions during the talk, it's fine if you interrupt me. So in healthcare, you take a lot of different images, different type of images. So here are some examples. And these images are, of course, used to diagnose different diseases. So it can be, it varies from, so here are some examples of microscopy images or pathology images where you look in detail on cell level on structures, and you have radiology like MRI or CT or SPECT, which are very different type of images where you can see the tissue in other ways. And then you could also have normal images if you're looking at skin cancer. It's more like the images we are used to from other domains. So even if we're working with different type of images or images from different modalities, and when using deep learning, we typically want to do some segmentation or detection or classification of this image or what is in the image. But independently of what type of image we have, there are some problems or challenges that are occurring in many of my projects working with medical applications. So often we have a limited amount of data, and that's because these are not images that anyone can capture. You need certain machines, and you need, if you're looking at disease, you need examples of persons who have this disease and images from those patients. So we cannot collect this data as we want. We need to be in a clinical setting to collect the data. Another problem is that there can be variations in the data, especially if we have limited variations in the training data. For example, if we only collect data from one hospital, we have a very limited training data set, and if we're developing deep learning tools, we might not expect this to generalize to other hospitals or other machines. And I will give examples of this, and I will also give examples of that we could have a limited ground truth, meaning that it's not always black and white, do you have this disease or not, or how you should grade this disease. There's variations in the healthcare. So I will give examples of this during the talk. So the outline for my talk, it will be focused on 5 projects, but I will mainly talk about the first and the last one. But since I want to give you an overview, I will also talk a bit about 3 other projects. So it's about cancer, prostate cancer, skin cancer, and breast cancer, and then dementia, working with Alzheimer's disease, and heart disease with coronary artery disease. So all of these are very common diseases, motivating why these why it could be useful to use AI to detect these diseases. So to start with, I will talk about prostate cancer. And this is a project I worked with a lot during my PhD. So I've been working with this project not all the time, but during 7 years for part of my time. And then we're working with microscopy images. So to start with, prostate cancer is very common. Approximately 1 in 6 men will get the diagnosis. And there is a lack of pathologists, at least in Sweden. And to grade this cancer using something called Gleason grading, which I will show you examples of soon. And this is like the best prognostic and predictive biomarker right now, but it is actually quite subjective and it has low reproducibility. So all of this motivates why having an AI-based tool to help the pathologists to reduce their workload or make the work more efficient would be very useful. And here are examples of how the images, what the images look like. So these are really high resolution images. So this is a prostate biopsy. It's about 10 to 15 millimeters long. And it's scanned in really high resolution, as you can see here. And the pathologist want to look at all the details in the image. So it's a lot of data to go through for the pathologist looking at just one biopsy. And then from each patient, you might have 10 biopsies. So it quickly gets a lot of data. And as I said, Gleason grading is used to grade this cancer. And it describes, so this is an example of a gland and how it is destroyed when you get cancer and it starts to spread in the tissue. So hopefully you can see this pattern also here, where you have the benign or normal tissue with well-defined glands when you get cancer. And these glands start to split up into smaller parts and when you get high grades of cancer. So it's very, advanced stage of cancer. It's more of a mess. You don't have any structure in the tissue. So when I started this project, soon 7 years ago, then these, here I have collaborated with pathologists in Malmö and they weren't working digital. So they didn't scan these images and looked at them at a computer screen. They looked at the biopsies or the slides in a normal microscope. So that was that's happened quite a lot during the last 7 years. Now they are digital in Malmö, working digitally with these images, but it varies a lot in the world and also in Sweden if you are doing this digitally or still using like the physical slide and a microscope. And this varies a lot, or working with these images digitally means some advantages, I would say, for the pathologists. So before, when the pathologist looked at this slide in the microscope, if they found something that was suspicious or was something that could be cancer, they used a normal pen to just draw on the physical slide next to the tissue. Here is something that is suspicious. I think you can see my pointer. I hope so. And then they took a ruler and measured how many millimeters and they think it was cancer. So it was not a very precise way to measure the amount of cancer. And it was not very easy to go back and look at the same cells again or show a colleague what they had been looking at if they weren't sure. So instead, when they are working digitally, so these green areas are drawn digitally. So you have digital annotations So there are benefits with that. And of course, that's if we want to use AI, we need to have this digitalized. And in this project, we have then collaborated with pathologists who have annotated a lot of slides for us. So they have drawn this type of annotations. So we know where is cancer in this biopsy, since in almost, or if there is cancer in a biopsy, typically there's a lot of healthy, normal tissue as well. So it's useful if we know where is the cancer, so we can work on smaller parts of the images. So just to give you a feeling of the number of data we have now in the end, 7 years later, we have data for training or developing our models from about 174 patients. So that's really not a lot. However, from each patient, we have more than one biopsy. So we have in total about 700 biopsies. And all of these biopsies are huge, or the images are huge. So if we extract smaller patches, we have more than 200,000 patches to train our networks on. So that's quite a lot in this medical domain. And what we want to do is to do classification of these smaller patches into benign or some Gleason grade. And the network here is just an example of a network one of the first we had when we didn't have that much data. And here I also printed our first results in 2017. We got some really nice results when we developed this and used a validation data to evaluate. We got an accuracy of 93%. But then we got some more data from another hospital and tested this algorithm and got an accuracy of 32%. So since we have 4 classes, this is just slightly better than random. So it really didn't generalize at all. And this is, of course, since we had a limited data set, both in number of images. I think it was about 200 images for, or like small parts of biopsies to train on. And these images were just from one hospital. So this limited data was caused by, well, that it wasn't digital at the moment, so there was no digital data. And also, I mean, it's still time consuming to collect this data, even if it's easier now when all the slides are actually scanned in the clinic as well. And then also that we need some pathologists to look at these images and say where it's cancer or not. And also that it's not obvious how you can share this data. So it can be hard to share the data and hard to get others' data. So we had a problem with generalization. So here are examples of images from different hospitals and with different grades of cancer. And what we saw in this first project was that we overfitted a lot to the training data. And we have differences between the hospitals due to, for example, different scanners. The stains, so I didn't mention this, but the tissue is stained with 2 colors. So they are pink and purple. It's hematoxylin and eosine. So they stain the tissue, the different parts of the tissue into different colors. And of course, these stains, if they're from different manufacturers, there might be differences. And then you have a lab where you actually stain the slides, and then you might have different procedures in different labs, or you might use different settings for the machines, etc. So therefore we get these variations. And those are no problem for a human, but if we're training our deep learning system on a really small data set, they cause a lot of problem. So I will mention now 3 methods we use to improve this generalization. Normalization, augmentation, and domain adversarial neural network, before I continue with some results. So to start with normalization, then the idea is that we try to make images from different hospitals look more similar. So the first approach we used was to use something called digital stain separation. So essentially you find the colors of the 2 stains and then you separate the image into 2 channels where you just have the intensity of the 2 stains. And then you can normalize these individually to appear to be, or to have the same color as an image from another hospital. Another approach is to use a cycle GAN. So I assume most of you maybe know what a cycle GAN is, but the idea is that you have 4 networks and they are trained simultaneously. 2 of those are generators, and they are translating an image from one domain to another domain and then back again. And then you have discriminators that are trained to tell whether this is a real image or whether it's a fake generated image. So we train these cycle GANs to translate images between different hospitals, essentially. So these are examples of original images from different hospitals, and then when we have normalized them to look like the other one. The second approach is to, instead of making the data look more similar, we try to expand the training data sets by using augmentation. So we know, or we can see that there is variations in the color, for example, and we think that this is the main thing here. So for the training data, we create new data to train on, where we artificially change the color. So we get more examples from each example we have. And for the color, this is easiest to do in the HSV color space, where you have just one channel, the U channel, to describe the color. So it's easy to just change the color. And then, of course, also you could add blur and noise, etc., as you probably do in other types of images as well. And the third approach was to use a domain adversarial neural network. And here is the idea to force the network, our classifier, to not look at features that we don't want it to look at or that are irrelevant. So the idea here, the top row here is our main classifier. We do some classification here, but then in the middle of the network, we take the features, and we have a second classifier, and this one is trained to, in our case, predict which hospital is this image from. So we want to be, we train this to be good at classifying for which hospital is this image from. But in between here, we have a layer where we reverse the gradients. So the first part of the network that's common for both classifiers will be trained to be bad at predicting from which hospital is this image. So in this way, we can force the whole network to be bad at saying which hospital or differentiate between different hospitals. But in the end, what we found was worked the best was actually using augmentation, so the easiest approach. So that's what we used. And here are some of our results. So this was a smaller evaluation study. We had just 37 biopsies. We got a really nice sensitivity. We wanted to have a high sensitivity, so 100% sensitivity on detecting slides with cancer. Specificity is slightly lower. But what we also did in this study was to evaluate and compare towards several different pathologists. So here you have the different biopsies, and then the different colors are either the algorithm, the blue one, the orange one is also the algorithm, but on a second scanner, or images from a second scanner. So we saw that we got the same result independent of which scanner we used. But then we also have results from 3 pathologists. So here we are looking at the amount of cancer on the slide, and we can see that it's quite similar, but it varies a bit, and it varies between pathologists. And then if we look a bit more in detail, here are just 4 examples of these biopsies, and for each of the biopsies, you have ABCD results. So we have 3 pathologists here. So 3 of ABCD are pathologists, and 1 is our deep learning algorithm. And the different colors are the different grades of cancer. So my intention here is that you could maybe yourself try to guess which one is the deep learning algorithm and which ones are pathologists. And maybe you will see that it's not that obvious. which one differs more from the others. And with this, I want to highlight that the ground truth varies a bit, and it's a problem here. So the solution for which one is the algorithm is that A is the algorithm, and the other ones are pathologists, and B and C are actually the same pathologist, but the annotations were done 1 year apart.
A question.
Yes.
Do you have a comparison between the three methods that you mentioned? You mentioned the augmentation and the normalization and the domain adversarial.
So I didn't include any results here, but we did this in a couple of different papers. So there are results. So in this, in the box here is one reference, and here is another reference where we compare the methods. We always compare to what's using augmentation. So in this last one, for example, we saw that using augmentation was even better than this domain adversarial neural network.
Okay.
Can I add a follow-up question there? Hey, I'm in the room with Olof.
Yes, sure.
I think it's really interesting. I'm working on similar problems, but not on medical data.
Yeah.
Did you compare with these? Did you compare these methods to just training a regular deep learning network on all domains at the same time, like regular empirical risk minimization? And if so, how large was the benefit?
So no, we didn't. And the reason for that was that we had almost all our data from just one hospital. And then we had some smaller cohorts from other hospitals. So if we should have trained on those as well, there hadn't been enough data to actually evaluate on those.
But what are different domains in this example? Isn't it data from different hospitals?
Yeah, exactly, different hospitals.
So why couldn't you have trained
yeah,
on...
I see what you mean here. Yes, so here we did, I'm not sure if I remember if we used only part of the data to train, at least for the domain classifier, or sorry, the main classifier, we only used data from our main hospital. So there we didn't use any other data. And for the domain classifier, of course, we used data from other hospitals, but we didn't use the labels from those images. So we didn't need any annotations. And I'm not sure if we used all the data or if we separated it.
Right, so a benefit of this algorithm using some type of domain adversarial thing is that the label is created by just saying that the images are from different hospitals, but you don't need the labels in the sense of which label, the label of the images themselves.
Exactly.
Yeah.
So in this example where we have these biopsies, if we have them scanned, we have a lot of data, but it takes a lot of time for the pathologist to annotate them. It could be very beneficial.
Right. Makes sense. Thank you. It's very interesting.
Great. Yes, so then I will continue with some more other results. These are not published yet. So it's ongoing work. We're working with the PRIAS cohort. It's Prostate Cancer Research International Active Surveillance. So this cohort consists of, it consists of patients who have prostate cancer, but just low grade or early stage cancer. So they have decided to not get any treatment yet. Instead, they are followed over time, gradually taking new biopsies and PSA values. So that's this active surveillance that you're continuously followed up. So then we have data from in total 147 patients, and about half of those got treatment during our study, and half of those haven't gotten any treatment yet. So they're still in active surveillance, and they regularly take new biopsies. So for these patients, we have biopsies from multiple occasions. And at each occasion, you take about 10 biopsies. So we have a total number of occasions, that's about 400. And since we take about between 4 and 15 biopsies, about 10 biopsies at each occasion, we have about 4,000 biopsies. And these we only use for evaluation of our deep learning algorithm. So this is a really, a nice cohort since there's so much data in one way, since we have so many biopsies, and in the other way, we don't have so many patients to work with. So it's still, a limitation. So looking at the labels here, we have just before we worked on like patch level or region level, where we have annotations and we know whether it's cancer or not. But here we don't have any such annotations. We can look at the whole slide level, whether there is cancer or not, and then they're summing up the Gleason grade in the whole slide. So that's called the Gleason score. And then we also have labels on patient level, whether this patient had cancer or whether this patient needed treatment. So it's a nice cohort. And some of our results, we mainly evaluated on biopsy level, since that was the easiest. So as I said, about 4,000 biopsies, and we got an AUC of about 0.92. And as I mentioned before, this problem with generalization, therefore we looked into images from different hospitals. So we had images from 3 different hospitals. Most of them were from Malmö, but some others as well. And we got similar AUC for all of those, so that's nice. And then we also had biopsies from different years, meaning that the staining could have changed. And all of those were scanned later on, since in 2011, there were no scanners. So they're all scanned on the same scanner, but we have variations in the staining appearance. So yeah, that was nice. And since we didn't have any annotations, or we couldn't evaluate on it on region level, we actually did some visual evaluation, just looking at the drawings. So here's an example. This is how a slide looks like. And this is the annotations from the pathologist. So they probably found some cancer in this area. And the cancer was Gleason grade 3. So that's why it says 3+3, and it was about 3 millimeters long. And then we compared these annotations with the output from our algorithm to see that we detected cancer in the correct regions as well. And we compared with different pathologists, since different pathologists had looked at those and got very similar results for different pathologists. So that's nice. And we compared with the percentage that the algorithm gives of cancer in the whole slide and the percentage that the pathologist estimated. So the length of cancer they found compared to the total length of the tissue or the biopsy. And there we also had a really nice correlation. So it seems to work well. However, we over-detected some cancers. So therefore we also looked into the true positives and false negatives. So if we look at the size of the cancer here first, we can see that for the true positives, we have a quite high cancer size if we compare to the false positives and false negatives. So when we either missed cancer or over-detected cancers, these were typically smaller areas. So that's kind of good that we're not completely off, but of course we shouldn't miss any cancer. And another interesting thing is looking at if immunohistochemistry was requested by the pathologist. So if the pathologist thought that this was a hard case, they weren't sure whether there is cancer in the biopsy or not, they can request to get a second section from the biopsy, but which is stained with this immunohistochemistry staining. And with this staining, it's much easier to see whether there is cancer or not in the slide. So they order this if they think that biopsy is hard. And there we could see, for example, that the false negatives, So the ones where we missed cancer, they requested this extra staining in more than half of the slides, and compared to the true positive ones where they order it for less than half of the slides. And similarly for the false positives, where we over-detected cancer, they also requested more immunohistochemistry slides compared to the true negative ones. Yeah, so there's a lot of different ways where how we can evaluate this. Yes, but I want to have time to talk about 4 more projects. I think I should go on. Now I will talk about Alzheimer's disease, and here this is an ongoing project, so I will not show any results, but I will describe the problem and give the idea how we are working with this. So Alzheimer's disease, as you know, it's very common. It's the most common form of dementia, and it's quite relevant right now since recently there are medications approved in the US, and they will probably soon be in Europe as well. And therefore it's extra important to early detect Alzheimer's disease so we know who should get these medications, who could benefit from those. So the goal with this project is then to identify future Alzheimer's disease dementia. And the diagnostic techniques that are used are cognitive tests. You take CT or MRI images. And in research, they also working with PET images, which are much more expensive, therefore not used in clinic, the CSF biomarkers and plasma biomarkers. Yes, and in this project, I have just been working with the MRI and cognitive tests. The goal is to predict if a person will progress to get Alzheimer's disease within 4 years. So we have both a binary classification problem here, will this patient get Alzheimer's disease or not? And then we also have something called mini mental state examination. So it's an examination where you measure the cognitive impairment of the person. So it's essentially just a set of questions that the person gets to ask and get asked. And then you get a score, and then you have this score at some baseline time and some follow-up time. So you can see the cognitive decline. And the participants in this study all had either subjective cognitive decline or some mild cognitive impairment. And we have some demographics information like age and sex. We also know how long the education level for the person, since this can be relevant for how, if you're trained to remember things, maybe you will be, you can reduce the effects of the disease, essentially. So we have these cognitive tests, and we have MRI images, and then we have a follow-up period. And we are evaluating different methods to predict those two, either progression to Alzheimer's disease or the change in MMSE slope. So we're using both the demographics and the clinical information and the MRI images. And the goal is, of course, that the MRI images, they have a lot of information, and we want to extract it using convolutional neural networks and deep learning, and hopefully get more information from these MRI images than we can get from just the clinical data. However, one problem then is if we look at our data, in total, we have slightly more than 300 participants. So it's a really small data set, and we have MRI images, which are 3D images. So it's really a lot of data in, but not so many examples, which is a problem when training deep learning. So therefore we looked at what has been done before, and we found an interesting paper where they had developed a parameter efficient deep learning approach for classification of Alzheimer's disease. So this is the design they used. They have the images and the clinical data as input. And then they have this parameter efficient network where they're using separable convolutions. And then they have group convolutions. So in total, they have quite a few parameters. So we actually managed to train this network with 3D images as inputs, although we have so few images. And furthermore, they trained this with multitask learning. So they had 2 tasks, predict whether this person had Alzheimer's or a healthy control patient. And also whether if they had a mild cognitive impairment, whether they will progress or whether they will be stable over time. So our idea is to use the same network, but with our data, and still use maybe multitask learning, but maybe we could add some other task. So predict this change in MMSE score, the slope. Also, we know that hippocampal volume is relevant for predicting Alzheimer's disease. So trying to predict this, we could regularize the network so we don't overtrain to our main task to predict conversion to Alzheimer's disease. So we will have a weighted loss then between these tasks. Yes, but as I said, it's ongoing work, so I don't have any results. So instead, I will continue with the 3rd project. It's about skin cancer, working with dermatology. And skin cancer is also very common. It's the most common cancer worldwide. And in Sweden, the incidence has increased dramatically last decades, and it's continued to increase. And this is, of course, we have pale skins. We are a lot out in the sun. We are not wearing sunscreen as we are supposed. So therefore, cancer is increasing. And the skin cancer can be divided into 3 subtypes. We have a malignant melanoma, as you probably know of. But then we have squamous cell carcinoma and basal cell carcinoma, and those are unpigmented skin cancers. Well, malignant melanoma is the most aggressive one, and it's about 90% of all skin cancer mortalities from malignant melanoma. But these unpigmented skin cancers, squamous cell carcinoma and basal cell carcinoma, they are super common, almost as common as all other types of cancer occurring in Sweden combined. So of course, these, even if they're not that deadly, they will burden the healthcare in Sweden a lot. And the dermatologist working with this and to set these diagnoses, they have a lot of different types of cancers, or there are different types of subtypes of these cancers. But if you just look at diagnosing if a lesion is malignant or benign, they had a sensitivity of 72% if you just look with the eye, and then they have this dermoscope. So essentially it's a special lens, and then they had some fluid between the skin and this lens, and they take a really high resolution image. So if they use this dermoscope, they get slightly better results, so 78%. However, there are also a lot of subclasses of these cancers, and if they should subclassify the cancer, the sensitivity is only 26% with just the eye and 33% with the dermoscope. So there's maybe the main motivation for this project, that we could really, or we would want to improve this performance. And if we have an AI that could work as a second opinion, maybe we could improve the performance. And another interesting thing is, you probably know that there's been some for malignant melanoma, a lot of work, and there's an app you can scan your own lesions, but there's not so much done for unpigmented skin lesions. But in the studies that have been done, they typically report the performance just independently of which skin type you have or which cancer type you have. And this is a disease that it's affected a lot of which type of skin you have. So there's a classification of how the color of the skin is essentially. And then also these more rare skin cancers. And that hasn't been used a lot. So in this project, we will do classification of unpigmented skin cancer. That hasn't been done that much. And we also want to do sub-classification of these unpigmented lesions. So this is an illustration of what the dermatoscope looks like. But yes, this is also ongoing work, so I don't have any results for this. Instead, I will continue with the fourth project, detection of coronary artery disease using myocardial perfusion imaging. So coronary artery disease is also very common. It's motivation for all my projects. Cardiovascular disease is the leading cause of death worldwide. It's estimated to represent 31% of all global deaths. And of these, coronary artery disease and stroke are estimated to correspond to 82%. So yeah, it's very common. And the disease means that you get a stenosis or a narrowing in one of the vessels that are supplying the heart with blood. And to diagnose this, you could use something called myocardial perfusion images or imaging. And those images look like this. So you essentially take an image of the vessels around the heart, and then you project it into this circular plot. So the three main arteries you have here are represented in different areas in these circular plots. So you can see the acronyms here. So based on these circular plots, they can say whether there's a narrowing in the vessel or not, or at least that's the goal. So a completely bright and yellow circle is typically good. And if there are darker areas, there might be some narrowing or ischemia. So one nice thing with this project is that we actually could have a ground truth, since the procedure in the healthcare is that you take the MPI images, the myocardial perfusion images, and if you suspect that there is a narrowing, you will continue with invasive coronary angiography. So this is invasive. It's not something you want to do if it's not needed. But there it's easier to see if there actually is a narrowing on one of the vessels. And then you can measure how small the vessel is compared to how wide it's supposed to be. And this is called QCA, so quantitative coronary angiography. So if you have a QCA value of 100%, it means that the vessel is completely blocked. But then we could use this QCA value as ground truth for when we are training our AI algorithm to, based on the MPI image, say how close if there is a narrowing in one of the vessels and how high the QCA value is. So that's nice. And we did this then based on the MPI images, and it could also be relevant with some additional features. So for example, the BMI of the patient, the age, and there's also some pre-test probabilities. So depending on your gender or age, etc., you have different risks of getting coronary artery disease. And we got really nice results on patient level to say whether there is a narrowing in any of the vessels. We get an AUC of 0.93. And that's really nice, since this is also an area where the assessment of these MPI images is a bit subjective. So having this as a support tool could improve the overall precision of the diagnosis. Yes. And then the last project is about breast cancer. So breast cancer is also very common. About 2 million are diagnosed each year, and 685,000 dies. And to be able to treat breast cancer, it's important that you detect it early. So here in Sweden, we have screening. So you can use mammography to screen to see whether there is something suspicious in the breast. And that works quite successful. And these mammograms are read by 2 radiologists called double reading. But in Skåne now, there is a study where they're evaluating using AI in the clinic. So they have an AI tool. It's a commercial system, and with this they get a score for each patient, and if they get a low score, it's only one radiologist that's looking at the image, and if they get a high score, they're still using this double reading with 2 radiologists. So this could really reduce the workload for the radiologists. Since this is used for screening, you take a lot of these images, so it could be super useful. Yes, but that's in Sweden, and that's not what I will talk about now. Instead, I will talk about that there are other parts in the world where you don't have screening. And the World Health Organization have highlighted this with the Global Breast Cancer Initiative. They want to reduce breast cancer mortality by 2.5% per year until 2040 and avert 2.5 million breast cancer deaths. And they have 3 focus areas, and one of those is access to timely diagnosis. So this project I'm working with is focused on this, access to timely diagnosis, and in settings where you don't have screening. So this project is called 23 Degrees North. There's actually a homepage if you want to look at it. And 23 degrees north is the latitude of the Tropic of Cancer. So if you look at the map is showing the mortality rate of breast cancer. And so the dark red areas are where you have a high mortality rate. And these areas coincides where you have countries with low or middle income. So you typically don't have any screening. So a solution in this setting where you don't have any screening, you don't have mammography, you don't have so much money to spend, could be to use a point of care ultrasound probe. So this point of care ultrasound probe, or pocket-sized ultrasound probe, as we also call it, is a really small ultrasound probe, which you connect to your smartphone. So you can see the images on the smartphone, and the probe is not larger than that you can fit it in your pocket. And it's quite cheap if you compare it to like the ultrasound machines used at the hospital in Sweden. They are a lot cheaper. So these could actually be used, we think, in these settings where you don't have any access to any diagnostic system right now. So what is our goal then with this project? Well, these images can be quite hard to interpret. It takes time to be a trained radiologist and analyze these images. So what we want to do is or are doing is to develop an AI algorithm to analyze these images automatically. So we can say, if you examine the breast with the point of care ultrasound probe, and then you can get an assessment from AI whether this is probably normal or whether this is probably something that needs to be treated. So that's the goal. And to diagnose these lesions, the radiologists look at different features of the lesions. So the shape of the lesion is relevant, the margin of the lesion, the orientation compared to the skin, and also if you have some patterns within the lesion or some features below the features. So if you could get enhancement below the lesion or a shadow below the lesion, that's also relevant. So here are some examples of ultrasound images. There are 2 publicly available small data sets that we have been using. The results I will show today, we have only used our own data, so it's collected here in Skåne. We have the conventional ultrasound images. So ultrasound is used in the clinic. If you suspect that there is something, you will check it with ultrasound and you, save the images. So we have both these type of images, and we also have collected our own images with the point of care ultrasound probe. So this is not used in the clinic. And in the data, we don't have any annotations, except, we only have annotations on image level, whether there is some lesion in the image or not, or whether it's benign or malignant. So yeah, in total, we have soon 700 ultrasound images and more than 1,000 point of care ultrasound images. And since the goal is to use this in the point of care ultrasound setting, we only set aside test images from this domain. Yes. So we want to use both ultrasound images and point of care ultrasound images to train this algorithm so that it works well on the point of care ultrasound images in the end. Yes, so the first thing was that we needed some pre-processing. For the point of care ultrasound images, there's a logotype, there's some text that might be confusing. So we just cropped the images to remove this type of information. And also depending on the shape of the probe, you can either you get a square image or you get this type of image. So for those images, we just cropped a square and we used zero padding if it wasn't squared. Yes, just to get all the images in the same setting. And then we looked at if there were some differences of the images from the 2 domains, and we saw that there was slightly more noise in the point of care ultrasound images, and they were also slightly darker or had a different distribution of pixel intensities. So I will not go into the details here, I think. And instead, I will mention that we used the CycleGAN once more to translate images between the 2 domains. So we translated our normal ultrasound images to so that they appear to be point of care ultrasound images. And we wanted to do classification, and we used these different combinations of data. So only using the point of care ultrasound images was like the baseline. And then we added augmentation. We added the ultrasound images and with augmentation. And then we used the CycleGANs to translate these ultrasound images into appearing to be point of care ultrasound images. And then finally adding augmentation as well. So this is our results, and that's quite a lot of results. So if we start at looking at accuracy and AUC, you can see that the accuracy is lower. And that's because we used 3 classes to calculate the accuracy: normal, benign, and malignant. But for the AUC, it was just cancer versus non-cancer, so it's an easier task. Secondly, if we look at the different types of input or data used to train, we see that adding the ultrasound images improves the performance compared to just using point of care ultrasound images. But using CycleGAN improved it even more. So that's nice. And then if we look at those pairwise, adding augmentation, we see that in all cases, adding augmentation is beneficial. And then finally, if we look at the different types of data used, and with augmentation, we see that we get the best performance using the CycleGAN generated images and augmentation, and an AUC of 95%. So that's a really good result. And then finally, we also analyzed these CycleGAN images slightly more and noticed that they had added some, depends on if you have a good screen, if you can see this small area, it's a bit bright down here. So in the original image, it was just a shadow, but here it has added something. And this could potentially change the label of of the image. So therefore we think that, well, this might be even better if we don't train the cycle GAN using all our data, but instead train one cycle GAN for each of our classes. Yes. So to summarize, there's a lot of applications where you can use machine learning. And I just showed you a few of them. And there typically are some obstacles or problems. And one of those is often limited data. And when we're using deep learning, we often want to have a lot of data. And also that data from different origins, they might have different appearances, and this could be really problematic. And then finally, also that the ground truth might be subjective, which could be problematic. Yes, and of course, there are many more people who have been working with these projects, so they should also be mentioned here. But otherwise, that was all for me, so thank you for listening.
Thank you, Ida. Do we have some questions from the audience? Was there a question? Otherwise, I'll start with a question.
I can have a question.
Yeah.
For the when you're having this cancer probes or the tests, there's a lot of white space, and the images can be quite large. How do you handle that? The cancer cells is maybe just a few pixels in a very large image.
Are you thinking about the prostate cancer example with the biopsies?
Yes.
So there we are, I mean, when training, we just crop areas where we know that there is tissue.
Are you doing that manually then?
No. For some of the data, we had areas where the pathologist had annotated where it is cancer and also normal tissue. So we knew where the tissue actually was. And otherwise, we just use like a threshold. It's quite easy to see which pixels are white and which are not. However, I had an example with a drawing with a pen on the slide. And that's problematic for our AI algorithm if there are drawings on the slide. How to handle those.
Okay, yeah, thanks.
Thanks.
I think you've mentioned that you've treated this as classification. You're classifying each image. Mm-hmm. So you have one label per image. Have you considered seeing it as a segmentation problem where you classify each pixel instead?
Yes, we have. But then we have looked at segmenting the tissue into like the tissue components, if it's a nuclei or whether it's the stroma around, or if it's the epithelial cells around the glands. But yes, we have done this as well. But doing like the cancer grading on cell level, I think it would be hard, also since the pathologists, I mean, there's variations in what they think is cancer, and they're not looking at just one cell, they're looking at like the structure of the cells, so it's not very precise where the boundary of the cancer is.
Hmm. Do we have some final question? Otherwise, thank you very much, Ida. This was a really interesting talk with some really important work.
Thank you.
Next week, May 11th, we'll have Jonathan Sauter from EPFL visiting us. He's going to talk about unsupervised deep learning-based 3D mapping from video and its applications to underwater mapping. So welcome back next week. Thank you. Goodbye.
Thank you.